All right, welcome back. Second track for today. Please welcome with me Alon Leviev. We will talk about attacks on Windows recovery.
Thank you. Thank you. Awesome to be here. So, good morning, troopers. I hope everyone are doing well. And welcome to my talk, Confused Recovery. So today I'll take you on a research journey into a new attack class targeting Windows recovery. This attack class includes several vulnerabilities and exploit techniques that, when chained together, allow fully bypassing BitLocker and extracting all the BitLocker protected data. So my name is Alon. I'm a senior security researcher working with the security testing and offensive research team at Microsoft, also known as Storm. My expertise is in vulnerability research, focusing on everything that happens before the operating system fully loads, so covering the various boot stages as well as their security features. So what's on our agenda today? We'll start with the research background and give an overview of both BitLocker and WinRE. And then we'll dive into the attack class itself, covering the internals, the vulnerabilities, and the exploit techniques. And we'll also see 2 demos at the end of this talk. After that, we'll discuss the mitigations that we implemented to block the attack class variants. And then lastly, we'll wrap up with some closing remarks. So to start, let's dig into the research background and set the context. So this research focuses on the Windows recovery environment, or WinRE for short. And to understand the research, we first need to understand what WinRE is and what role WinRE plays in Windows. So WinRE is the Windows recovery platform. It's designed to address critical system issues, such as startup failures, persistent crashes, BitLocker errors, and more. For instance, if your machine crashes, WinRE is the component that is responsible to analyze the crash, identify any issues, and then fix them. Architecturally, WinRE operates with its own standalone OS, known as the Recovery OS. That Recovery OS is a lean version of Windows with recovery-specific customizations. These customizations, the recovery-specific customizations, include a unique set of recovery tools that are all integrated into the known blue-screened recovery UI. Now, for storage, the entire Recovery OS, including all the executables, DLLs, drivers, all the system files, they're all compressed into a single WIM file named winre.wim. And this WIM file is typically stored on disk on a dedicated recovery volume. Now, when WinRE boots, the entire WIM file is decompressed into RAM, creating a RAM disk that hosts the Recovery OS runtime. Now, any changes made within this RAM disk, within this environment, within WinRE runtime, are not saved back to the original WinRE WIM file, making the Recovery OS inherently volatile. So modifications to the RAM disk are discarded upon reboot. And this is an important note for any WinRE research. Right? Any changes are not saved back. So to boot into WinRE and interact with it, physical access is typically required. A physical user can do this by holding the Shift key while selecting restart from Logon UI. And then the user can interact with the recovery environment and trigger the tools that he desires. So now that we know WinRE can only be accessed by a physically present user, the key security question that we asked ourselves was, which security guarantees still matter in the presence of a physical user, of a physical attacker? And so while a few Windows security features remain meaningful against physical attackers, the one that directly intersects with WinRE is BitLocker. So to understand how this connection plays out in practice, we first need a quick refresher on what BitLocker is and what exactly BitLocker protects. So BitLocker is a full volume encryption technology that is designed to protect individual disk volumes. Once enabled, it encrypts the target disk volume that the user chooses, or by default, the OS volume, protecting all data stored on it. And as we said, by default, it targets the OS volume, meaning that all the data stored on the OS desktop, so downloads folder, desktop, and all sorts of sensitive data that you store on the OS is encrypted by BitLocker. So with BitLocker encryption in place, the data stays protected, even if an attacker gains physical access to the machine, for example, by stealing the device or stealing the disk and then trying to access that offline, because the data is always encrypted. Now, unlike other Windows security mechanisms, which assume an attacker is already authenticated or log into the machine and attempting actions like privilege escalation, BitLocker is designed for a different use case, defending against someone who has the machine in their hands, but no ability to log in. So simply put, a thief, a stealer. From a physical attacker's perspective, this is where things, the intersection of WinRE and BitLocker get interesting. So under certain conditions, WinRE is allowed to fully access the BitLocker protected OS volume. And if WinRE has full access to a BitLocker protected volume, then any vulnerability in WinRE could potentially be leveraged to extract the protected data. But the access that WinRE gets isn't unconditional. It depends on specific safeguards that are being put in place. So WinRE's access to the BitLocker protected OS volume is gated by two conditions. One is about the integrity of the recovery environment itself, and the other is about which recovery tools are allowed to run once inside of WinRE. So let's walk through how each of these conditions is enforced. So to verify the integrity of the WinRE WIM file, a feature called trusted WinBoot is used. It computes the hash of the loaded WinRE WIM and compares it against a known trusted hash, so a simple hash comparison. And then any modification to the offline WinRE WIM after the hash has already been saved will just cause a loss of trust, and it means that a BitLocker key will not be released for that untrusted WinRE instance. So if the hashes match, the OS volume is unlocked. If they don't match, the OS volume remains locked. In the unlocked state, WinRE has full access to the volume, and in the locked state, WinRE has no access at all. So this locked, unlocked state and the integrity of WinRE fully determines what WinRE can and cannot see during the recovery that it performs. Now, even with the trusted WinRE image, not every recovery tool should get full OS access, right? Because there are some recovery tools that are overly permissive by design. So if an overly permissive tool in WinRE is invoked, even when WinRE is trusted, WinRE would immediately relock the OS volume to prevent unintended data exposure. And that relock happens before the tool is being launched. A concrete example of such tool that will result in a relock is the command prompt, which provides broad and unconstrained access. So if you choose the command prompt from the WinRE UI, WinRE will request you to insert the BitLocker recovery key, and if you don't insert that, it relocks and launches the command prompt. Now, with these two safeguards in place, the research scopes and constraints became more well-defined. So no static modifications to WinRE WIM are allowed as part of any attack, as they would break the WIM trust, and any recovery tools that trigger relock are excluded from the research scope. So this is important not only for this specific attack class, but for any WinRE research that any of you might want to perform in the future. So with better knowledge about WinRE, BitLocker, and their intersection, the security boundary as well, let's dive into the attack class internals. So as we delve into WinRE and analyze the way that it works, we found that WinRE places full trust in the target OS volume that it is meant to recover. As part of the recovery process, WinRE often reads sensitive configuration files directly from that target volume that it recovers, assuming that they're out of an attacker's reach. This trust model is in fact intentional. So when BitLocker is enabled, a physical attacker cannot read or modify the OS volume because it's encrypted by BitLocker. And so WinRE does not need to validate the data that it consumes from that encrypted OS volume. And that's the reason that it reads sensitive files or stores sensitive files in that volume. However, this trust assumption, if ever violated, creates an interesting opportunities for abuse. So we set out to explore what happens when this trust assumption is broken and how it can be abused. We found that the target OS volume is searched for twice during the system lifetime. The first time is during the boot phase by the boot manager, which needs to unlock the target volume for WinRE to have access to it. That's happening as part of the trusted WinBoot procedure. It verifies the integrity of the WinRE Win file, and then it needs to know what WinRE needs to recover so that it can unlock that volume, transfer the BitLocker key to that component, and then when WinRE does the recovery, it shouldn't ask the user every time for a recovery key. So the first time happens during boot for that reason, to unlock the target drive. The second time is during WinRE runtime, which needs to know which exact disk volume it needs to recover. So essentially, both the boot phase and WinRE phase both are looking for the same type of information for different purposes. The first one is to unlock, the other one is to recover, but that's the same type of information. But importantly, the boot phase doesn't transfer the unlocked volume to WinRE. And not only that it doesn't transfer the unlocked volume to WinRE, the lookup functionalities they're not shared. So each phase implements its own implementations. And although they mostly are based on the same data stores, because these are separate implementations, a small diff in the implementation could create interesting opportunities. So we asked, what if these implementations, boot and WinRE, fall out of sync, if they're not sync? So as we said, any major difference would allow us to confuse the boot phase with unlocking the BitLocker encrypted volume, while having the WinRE phase recovering an attacker-controlled volume. And as a result of that setup of the confusion setup, all the sensitive files that we've mentioned that WinRE reads from the target volume, or that are typically out of an attacker's reach, would be fully controlled by us. And this exactly was our goal. Now, there are two important constraints that must be met for this attack to work. The first constraint is that the boot phase lookups must always unlock the BitLocker encrypted volume. No matter what happens, they must unlock the BitLocker encrypted volume so that we have access, so that WinRE has access, right? If they don't, it's game over. No matter what we find, we don't have access to the BitLocker secrets because they're locked. The second constraint is that WinRE phase must recover an attacker-controlled volume. This constraint is critical too, right? If WinRE doesn't recover an attacker-controlled volume, we have no influence over the configuration and data that it queries. And by saying an attacker-controlled volume, I mean it could be the recovery volume, which is not encrypted or protected, the EFI volume, or even any volume that the attacker can add to the disk, right? There's no prevention for adding custom volumes to the disk. So that's the general idea. And these are the two constraints. So with a better idea of the attack class, its goals, constraints, the research steps were quite straightforward. First, we need to identify volume confusion primitives that meet all the required constraints that we've just mentioned. The more primitives we find, is the better. The second step was to build on these primitives, showing how they could be exploited to bypass BitLocker and extract BitLocker protected data. Now, we knew as part of this research that WinRE does query sensitive files from the target volume, but again, this attack class was not something that anyone has previously explored, and so it was our focus to also prove that something meaningful can happen by controlling these files, and essentially, we needed to bypass BitLocker with it. We couldn't just say it happens and fix it. So we needed to actually prove that it can bypass BitLocker. So with that, let's now look at the first stage of the research, which is looking for these primitives. And in order to look for those primitives, we need to look at the boot phase lookups and WinRE lookups to analyze their implementations. So now I'm going to walk through the boot phase lookups and how exactly they find the target OS volume. So the boot phase lookups are based on the boot configuration data store, or BCD for short. The BCD store contains Windows boot configuration, and it is stored on the EFI volume, which is not encrypted or protected, and is accessible to a physical attacker. So as you can see on the monitor, this is the typical volume layout on a Windows machine. BCD is on the EFI volume. The middle volume is the OS volume, which is encrypted by BitLocker. And then we have the recovery volume, which is where WinRE gets written from. So BCD is on the EFI. Now, the BCD, in terms of format, is essentially a list of objects, and each object contains elements as key and value pairs. It's consumed during boot by boot components, which read those elements, objects, key and value pairs. So the possible value formats are predefined structures of either device, string, GUID list, integer list, or Boolean. These are the typical types that an element value can have. So on the monitor, you can see a screenshot of a BCD object layout. On the left side are the element names, and on the right side are element values. So, for example, the first element is an identifier, right? And it is of type GUID. And as you can see, the value of it is a GUID. Then you have a device element with the value of partition equals C. Under the hood, this is a device structure. And then you have some others, for example, locale is a string, description is string, path is string, and so on. Now, before I move on, I do want to give an important note, is that specific BCD properties are disallowed when BitLocker and Secure Boot are enabled, which for our research, we assumed that both are, of course. We don't want to cut any corners. And the reason that I mention it is, in our research, we didn't encounter any change that triggered a forbidden element. So we're not going to cover exactly how some elements are protected. But if you want to perform further research, you should be aware that some of them are validated. For example, boot debugging is an element that is always forbidden when Secure Boot and BitLocker are enabled. Right, so the code behind the boot phase lookups is quite long and complex, so rather than going line by line about how it works, I'll just explain the exact lookups that are happening during boot using some diagrams. So on the screen, you can see 3 BCD objects. On the left is the boot manager object. In the middle is the main OS object. That's the OS, probably, for example, your OS, the one that you're using. And then on the right is the WinRE OS. For example, you can see that the main OS has partition C as the OS device. Its recovery sequence is WinRE, and so on. Descriptions fit. And so these are the 3 objects that boot manager operates on. So let's assume boot manager is currently booting WinRE, and you can see that the booted entry is the right one, the WinRE entry. The boot manager would first check whether the trusted OS device element is present in the WinRE OS BCD object. You can see the highlighted lookup. The lookup that is performed is highlighted. If that element is present, the boot manager unlocks the reference device, and the lookup process stops here. Now, for this demonstration, because I want to show you the entire lookups that are performed, we'll assume that this element is not present. But if it was present, what it would look like is, for example, partition equals C. And then when boot manager sees that, it just unlocks the C drive and continues the boot. Now, if that element is not present, the boot manager queries the display order element, which contains a list of BCD objects. It then iterates through each entry in that list and applies additional filtering. In our case, the display order, as you can see, contains a single GUID. That's the main OS GUID. And so the subsequent checks that are performed by the boot manager are on that specific GUID, which is the middle object. So the first check that the boot manager performs on the iterated entry is whether the booted entry, which is the WinRE OS, is listed in the recovery sequence of the currently iterated entry. Now, the reason that it does this check is because when we fail to boot a main OS entry, the recovery works, the boot manager would simply go to the recovery sequence and execute that entry. And so that's kind of a backward check to make sure that WinRE that's currently being booted is somehow related to the iterated entry. Now, in our case, this check passes. As you can see, recovery sequence contains the WinRE OS GUID. Next, the boot manager verifies that the iterated entry has device path and description elements. It just does some sort of sanity checks that this object is actually valid. So it doesn't validate what contents the device path or description elements contain. It just makes sure that they exist. So if all these checks pass, as they do in our case, the boot manager treats the iterated entry as the one associated with the current WinRE boot, and the device to unlock is the device specified in the OS device element, which here is the C drive. As a result, once the boot phase finishes, it can freely access that volume because the boot just unlocked it. But do you remember that the boot phase does not transfer the unlocked device to WinRE runtime? Instead, once WinRE starts, it performs its own lookup again, as we previously mentioned. In the traditional WinRE state, the target volume is resolved from BCD, much like during boot. And in the automatic repair state, when, for example, there is a failure that needs to be automatically repaired, the target volume is not resolved from the BCD directly, but from the BootStat log file. So let's walk through the BCD-based lookups in the traditional state that WinRE performs. So WinRE, when it starts executing, it first enumerates the disk volumes to locate the BCD store. After finding one, it performs an additional BCD queries to resolve the target OS. So you can see that's a pseudocode, but generally it uses two Windows API, find first volume, find next volume, iterates over the volumes, and checks for a hard-coded path, EFI Microsoft boot BCD. If the path exists, it performs the lookups on that store. Now, in terms of what exactly is being looked for in that store, so WinRE first queries the display order, much like the boot, and iterates over the list of entries. In our case, only main OS is there. It then verifies that the current WinRE OS appears in the iterated entry recovery sequence. Again, that's a check that was performed during boot as well. But finally, it resolves and recovers the device specified in the OS device entry. In our case, that's the C drive. But if you remember the previous lookups, there are some missing steps in the WinRE lookups. So the three key differences between the boot and WinRE lookups, I'm talking only about BCD here, is the first one is that WinRE does not use the BCD store from the EFI volume directly. It does this volume iteration logic that we just shared in the code snippet instead of using EFI store directly. Second, it doesn't consider the trusted OS device element that the boot phase does check. And third, unlike the boot phase, WinRE doesn't check the validity of the objects, so it doesn't filter out entries missing device, path, or description elements. And these differences introduce multiple opportunities for volume confusions. So let's walk through a few primitives that we found by abusing these differences in lookups. So the first issue lies in the volume iteration logic, which is used to locate the BCD store. So internally, functions that are used are find first volume and find next volume. And after we've read their documentation, we found an interesting note in the remarks section. So the remarks section highlights a very interesting point. I'm going to read it out loud. It says that one should not assume any correlation between the order of the volumes that are returned by these functions and the order of the volumes that are on the computer. So there is no correlation, right? These APIs perform further filtering under the hood. So let's compare the physical volume ordering and what is actually returned. So the physical volume ordering is what probably a developer would think would be returned by these APIs. In most cases, physical volume layout is first the EFI volume, then OS volume, and then the recovery volume, the last volume on the, in the layout. If that was true, by the way, then there would be no issue, because the EFI volume would be encountered first, and it contains the correct store. So even though this logic is not accurate, if the volume that is returned is the physical order, there would be no issue. However, the order that is actually returned by these APIs is first the OS volume, then the recovery volume, and then the EFI volume. Now, given this iteration, an attacker can place a custom attacker-controlled BCD store on the recovery volume. And since the recovery volume is checked first, the store is treated as valid. Right? So you can see here the layout. The store that was used to boot the computer is in the EFI volume. But then the attacker-controlled one is in the recovery volume, and the iteration is first OS, then recovery, then EFI. And the reason, by the way, that we can't place this store on the OS volume is because it's encrypted by BitLocker. Now, what's cool about this primitive is that this store isn't used by the boot, right? It's only WinRE uses that store. So even validations that are performed during boot, although most of the elements are used during boot, so when WinRE says that, it's mainly enumerations and not actually actions, but when WinRE says that, this is not something that the boot even is aware of. So once we arbitrarily control that BCD store, we can create a malicious BCD object inside of that points to an attacker-controlled volume and passes all WinRE lookups. And this setup enables our first confusion primitive. So what do we do inside that attacker-controlled store? We create a malicious OS BCD object. We changed its OS device to an attacker-controlled volume. In our case, we set it to OS partition equals D. It can be anything. D is mostly the mounted recovery volume in WinRE. That's the reason that we set it. And then we place the recovery sequence to have WinRE as well, so that the other checks are passed. Now, let's assume that this issue of the iteration logic is fixed. Even if WinRE is only using the EFI volume, additional differences are still there. So that leads us to the second issue, which is that WinRE ignores the trusted OS device element, while the boot phase doesn't ignore that. So an attacker can set that element and reference it to a BitLocker encrypted volume, while creating a malicious OS object whose OS device points to an attacker-controlled volume and still passes all the checks. As a result of these setups, and again, the changed elements are the ones highlighted. So as a result of this setup, during the boot phase, the boot manager honors that trusted OS device and unlocks the referenced volume. In this case, that's the BitLocker encrypted volume. We set it to the volume that we want to extract secrets from. And then later, when WinRE performs its own lookups, it ignores that element and then resolves the malicious OS object instead, treats the attacker-controlled volume as the recovery target. And that is the second primitive that we found. Now, even if that primitive was fixed, and WinRE would honor the trusted OS device, other differences still enable another confusion primitive. And this leads to the third issue, which is that WinRE does not filter out missing device path or description elements, while the boot phase does. So an attacker can create a malicious OS object without a description element and point the attacker to an the OS device to an attacker-controlled volume. Then what it should do is prepend that malicious object to the display order so that first the malicious object is encountered and then the main one. As a result, during the boot phase, the boot manager evaluates the malicious entry first, right? It iterates over display entries, and so first it encounters the malicious one, but it would skip that malicious entry because the description element is missing. So it then proceeds to the main OS entry, unlocking its OS device, which is the BitLocker encrypted volume. And then when WinRE later performs its own lookup, it encounters the same malicious entry first, but it does not enforce the description check. It treats this as valid and proceeds to recover the attacker-controlled volume. So that's the third confusion primitive that we found. OK, so far, we've covered 3 issues in the lookup logic used by the traditional WinRE flow. And by saying traditional WinRE flow, when WinRE boots to the normal recovery UI, but not to the automatic repair flow, which has different lookups, as we mentioned beforehand. So let's move on to understand how WinRE finds the target OS in automatic repair logic. So in this case, WinRE relies on a file called BootStat. Instead of iterating and validating BCD objects to determine the target volume, it parses that BootStat file. It reads an object GUID from that file, and then a BCD object GUID from that file, and then directly uses that object's OS device as the target value. So it's not that we don't use BCD at all here, it's just that the way that we find the target object GUID identifier is from BootStat and not from BCD iterations. And now you will understand exactly why we do it. So let's take a closer look at the BootStat internals. So that BootStat file is the Windows boot status data log. The way it works is that boot components record boot time events into this log, and then runtime components, for example, WinRE, later read and parse it to understand what happened during the boot process. So it's simply a log that can be used for analytics later in runtime. There are 2 instances of that BootStat log file. One is maintained by the boot manager, stored on the EFI volume, which is accessible to an attacker, and then the other one is maintained by the bootloader and the OS, and stored on the OS volume. Now, both instances serve similar purposes, and they also share a name, but their file formats are not identical, so they're not one-to-one file format. For WinRE lookup specifically, only the boot manager's BootStat is used, and so the following explanations apply only to that instance. When WinRE parses that BootStat file, it reads that from the EFI volume, and then it looks for boot up launch events. These events are inserted into the log by the boot manager for every boot application that the boot manager launches. So for example, if the boot manager launches the bootloader, winload.efi, it immediately, as part of the launch, would log an event into BootStat. The format of the event that the boot manager logs is fairly simple, so each entry includes an application ID, which represents the BCD object GUID of the launched application. It also includes a launch reason, which represents the reason that the application was launched. And there is also the application path, which represents the full path of the launched application. So it's a fairly simple structure. Now on the screen, you can see the two launch events that would appear in the log when automatic repair is triggered. So let's walk through that for a second. So let's assume that the main OS entry is corrupted and can't be executed. You can see that its application path is not here at EFI. So when boot manager tries to execute that, it would, of course, fail. So the boot manager will record an event for that entry. That's the first one on the index. When that launch fails, the boot manager proceeds to launch the recovery sequence of the failed entry. So you can see that the second entry the second application is the WinRE one. And the launch reason is automatic repair. Then when WinRE starts, it first reads the last event. And it sees what's the launch reason. If it sees that it's automatic repair, WinRE knows that it should execute the automatic repair. And then after it sees that it's in automatic repair mode, it immediately goes back one event to determine which OS should be repaired. So WinRE then looks for the launch event that occurred just before its own. In our case, that's the first one, corresponding to the failed OS launch. And WinRE reads the application ID, reads the corresponding BCD object, and directly uses its OS device element. Now, the reason that we use BootStat here is because automatic repair, right, things probably went wrong in the boot. And one of the things that could went wrong is, of course, the BCD layout and so on. So that's the reason that we use BootStat in that case. So with that in mind, we understand that controlling the last two launch events in BootStat could give us another volume confusion primitive. However, a few challenges popped. So the boot manager appends new launch events to BootStat on every boot. It's not a functionality that can be disabled or something by design. WinRE consumes only the two most recent entries, which makes it harder to control these events arbitrarily, which is what we need. So there are two possible approaches to find a way around it. The first one is we can try to prevent, by finding a flaw or a bug, prevent the boot manager from writing new launch events on every boot. And then the second one is we can attempt to craft specific boot sequence that, once executed, shapes BootStat to contain the launch events that we want. Now, both approaches are probably possible and feasible, but in this talk, we'll focus on the first one, which is trying to prevent the boot manager from writing to the log by finding some sort of bug or a flaw there. So after digging into the boot manager's logging mechanics, we found that during the log initialization, the boot manager treats the log as valid only if its size is exactly 65,536 bytes, no more and more less. So the size of that file is hard-coded. It's always the same size. And it's a cyclic log, right? So it's, that's the reason that it's hard-coded. Now, if the size of the log doesn't match, the log is considered invalid, and no launch events are written to it. Now, what's more interesting here is that WinRE does not enforce this size check, and will accept BootStat of any size. Right? So this is another difference in the way that WinRE sees the OS and by the way that boot manager sees them. So to arbitrarily control the BootStat, we can craft an attacker-controlled log and ensure that its size is different from the hard-coded size. It's different from 65,536 bytes. We can just add a few bytes, a few junk bytes in the end of it. And the result would be that the boot manager just stops writing new events to that file, while WinRE will parse and consume it normally. So with that, we have our fourth confusion primitive in hand. The setup is quite straightforward. We create a malicious BCD object in the BCD store, OS device pointing to an attacker-controlled volume. Then we craft a BootStat file with the most recent launch event as auto-repair, and preceding launch event references the malicious object GUI. So that's the general layout of the indexes of the events and also the malicious object. Note that this primitive has one limitation, and that limitation is that with this setup, WinRE automatically executes automatic repair, starter repair tool. And it means that we will have to find a way to exploit that tool, otherwise this primitive instance would be useless. So the other three primitives that we found allow us to gain that primitive with any tool inside WinRE. But this one specifically has only one tool that is possible to be executed, and it's being executed automatically. All right, so now to the interesting part. We've covered 4 different ways to achieve volume confusion primitives in WinRE. Now the real question is, why do these primitives matter, and how can they be used to bypass BitLocker? So to answer that, we focused on identifying WinRE flows with specific characteristics that make a bypass feasible. We essentially define some characteristics that if we find the flow that meet these characteristics, it will make it more likely that we're able to bypass BitLocker by using this flow. So the characteristics were, first is a flow that must be triggerable either through the WinRE UI or via the RAgent XML file through scheduled operations or automatically during the WinRE startup. So just a flow that is triggerable. Second is a flow that must not relock the volumes, since WinRE relock mechanism would immediately revoke access to the BitLocker secrets, which we've worked so hard to keep them in memory. And then the third is that the flow must read configuration files from the target OS volume in order to perform sensitive operations, because now we control that volume. So the core idea, what we've had in mind, is to combine such a WinRE flow, if we find one, with the volume confusion primitive, allowing sensitive operations to execute while the target volume remains in an unlocked state. After exploring different WinRE flows, we found two potential candidates, the push button reset tool and the startup repair tool. So let's start with the push button reset tool, or PBR for short. So for those of you who are not familiar with what PBR is, it's a built-in system reset mechanism. It allows users to reset their system and supports multiple modes, for example, keeping or removing user files, reinstalling the OS from a local or remote source, and more. And that's the PBR UI resetting this PC. I'm sure most of you have seen this UI before. Now, one of these PBR modes, because as we said, there are multiple modes, the one mode that is known as online PBR meets all the conditions that were required for successful exploitation. So it can be triggered freely as a scheduled operation from the XML file. It does not invoke the volume relock functionality, and it queries configuration data from the target OS volume to perform sensitive operations. Now, what exact sensitive configuration does it query? So specifically among the PBR configuration files is an XML file named reset_session.xml. This XML file defines the full set of operations executed by PBR, so it's like an action list. So when PBR executes, it just follows the actions that are written in that file. Now, notably, this file contains the decrypt volume directive, which instructs PBR to decrypt an arbitrary BitLocker encrypted volume. And as you can see, we can set that target volume to any volume that we want. So we can set it to C, D, or anything. So to tie everything together, here is the full flow for bypassing BitLocker. So first, we place the PBR configuration, all the files that are required. We're not going to go one by one because it's quite long. But we placed all these files under the sysreset directory on the attacker control volume. Then in the reset session XML, we added the decrypt volume operation, which is pointing to a BitLocker encrypted volume that we want to extract the secrets that are on that volume. Next, we use the volume confusion primitives to force the boot phase to unlock that encrypted volume while WinRE operates on the attacker-controlled one. Then we trigger online PBR, and as a result, after that attack, the BitLocker volume will be encrypted, and we'll be able to access it. So now, let's see a demo. In this demo, I'll show chaining the first primitive with that PBR exploit technique. All right, so we have a locked machine, which we don't have the password to, simulating a BitLocker scenario. We shift restart to get into the WinRE platform. Once we're inside WinRE, we select Troubleshoot, Advanced Options, and Command Prompt. Now the recovery key is requested, which of course we don't have it, so we skip the drive. And as a result of skipping the drive, you'll see that we have no access to the C drive. And if we check what's the current status of BitLocker, we'll see that protection is on, but the drive is locked. So now we change drive to the D drive. That's the mounted recovery volume where we placed the exploit beforehand. That volume is accessible to anyone. We executed the exploit. And then we are going to restart into WinRE for PBR to take place. Now you will see the PBR UI, so the reset operation taking place. Under the hood, what happens is that PBR currently tries to reset an attacker-controlled volume. It essentially reads the configuration file from there, the reset session XML. It sees that it has the decrypt volume directive. And then as a result of that, what you see now, what happens now under the hood here is that PBR tries to actually decrypt the volume that we've set in that XML file. And that's the reason that it takes so long, right? Decrypting an entire volume is taking a long time, so we speed it up a little bit. Now, when PBR finishes executing, we're going to go back into the main OS. And we still don't have the password to the OS, but we're going to shift restart into WinRE. And now we'll check what's the current state of BitLocker, what's the current status of it. So we select command prompt. You can see that the recovery key is not requested here. If we change drive to the C drive, you can see that we have full access to the C drive, which was protected and encrypted by BitLocker. And if you wonder why this access is possible, we'll check what's the current status of BitLocker. You'll see that the protection is off and the drive is fully decrypted. So we're able to fully bypass BitLocker by essentially disabling it on an arbitrary volume. Thank you. So let's now move on to our second exploit candidate, which is SRT, the startup repair tool. And that's the tool that is being executed as part of the automatic repair flow. So SRT is the built-in repair mechanism. It runs when the system fails to boot or experiences repeated crashes. SRT also met all the conditions that were required for successful exploitations. Luckily, again, because as we mentioned, one of the primitives only runs against SRT. So SRT can be freely triggered if we control BootStat, which we proved that we can fully control. It does not invoke the volume relock functionality. And for the third requirement, it actually doesn't only query configuration from the target volume, it actually executes an executable from that volume. So the SRT procedure performs many diagnosis functions. It checks many things to understand what went wrong. Among these, it checks if the page file contains a kernel crash dump. Then if a crash dump is detected, SRT uses WhereFault to process that crash dump. Critically, both the page file and WhereFault are being read and used from the repaired volume. And no signature checks or validity checks are performed. So to tie everything together for the SRT exploit, here's the full BitLocker bypass flow. So first, we place the required SRT configuration and supporting files on an attacker-controlled volume. And this includes the attacker-controlled executable placed at Windows System 32 WhereFault.exe. Could be any executable. And you also need to put the page file containing the crash dump at the root of that volume. As again, that's the general layout, WhereFault page file and additional SRT configuration. Next, we use the BootStat-based volume confusion primitive to force WinRE into repairing the attacker-controlled volume and trigger SRT. And as a result, the executable that we've controlled is executed, allowing code execution within WinRE and enabling any actions that we want, for example, dumping the BitLocker recovery key or spawning an interactive shell. So let's see a second demo of chaining the BootStat primitive, confusion primitive, with that SRT. So again, we have a locked machine, which we don't have the password to. So we shift restart to get into WinRE. Once we're inside of WinRE, we select Troubleshoot, Advanced Options, and Command Prompt. Recovery key is requested here. We don't have that key, so we skip the drive. And you'll see that access to the C drive is not allowed. So we change drive to the D drive, execute the exploit that performs the BootStat confusion primitive and then places all the files that are needed, and then we reboot into WinRE. Now, SRT will now be executed. You will see that it says diagnosing this PC. And the file that we've placed instead of WhereFault is an arbitrary file that spawns a message box. And then once that message box is closed, it spawns a command prompt. So let's see what happens now when the diagnosis and repair is running against an attacker-controlled volume. You can see a low from Storm. Press OK. Then command prompt, change drive to the C drive. We'll list the contents of the C drive. You can see that all the contents are there, including the secrets.txt file. And also, if we want to, we can also dump the BitLocker recovery key. As you can see, we use the manage BDE command. We can note that key, and then we can even extract the disk and perform operations offline. So Thank you. All right, so we've talked about attacks and exploit, and now let's talk about the mitigation for the attack class. So after identifying multiple volume confusion primitives, we realized that there were likely more to be found and that fixing them individually wouldn't scale. So together with the engineering teams, we looked for a structural mitigation, one that would close the gap rather than address individual cases one by one. We've had few options in mind, and then the mitigation that we've ended up with implementing enforces a simple rule. Once WinRE identifies the target volume, and before launching any recovery tool, it relocks all the volumes other than the target volume. As you can see, the before mitigation state, if WinRE recovers the recovery volume, the OS volume remains unlocked. But the after state, WinRE recovers the recovery volume or any other volume, all other volumes are going to be relocked immediately. So before that mitigation, it was possible to create weird scenarios where WinRE recovered one volume while another remained unlocked, and this state can no longer be created. And as a result, any additional volume confusion primitive that is found is no longer effective. Regardless of the exploit path, BitLocker protected data can no longer be accessed. So to wrap things up, let's quickly go over the research results, discuss the main takeaway, and conclude. The CVs for the attack class variants are on the monitor, so 4 CVs were published. Fixes were shipped in July and October patch Tuesdays in 2025. This research was also part of a broader security review that we did on WinRE. In total, we had 11 CVs for BitLocker bypasses that we found. If you're interested in learning more about the other findings, check out our BitUnlocker talk and Recovery Reimagined talks, which include additional findings. And the research results brings me straight into the takeaway of this talk. It's critical to assess and challenge foundational assumptions made by the research target. This research uncovered a significant attack class by questioning WinRE's trust in its associated OS volume. Now, while BitLocker encryption makes this assumption appear secure on the surface, flaws in the implementation revealed vulnerabilities that undermine this core trust model, and without deeper analysis, this attack class would have remained undiscovered. Thank you very much.
All right, are there any questions? Yeah.
Thank you. Yeah, great talk.
Thank you.
I feel like we don't find new attack classes every day. Do you think there's going to be maybe a new sub-attack class, something like Spectre, like Spectre v1, v2, where the mitigation patches this attack class, but that there another one might come up or in a similar area from your expertise?
I mean, if I've had an idea in mind, I would probably check it already. So in my eyes, because that happens really early in the WinRE phase, and because it relocks all the volumes, then it's hard for me to see ways to bypass it. But then again, as in security, there are always some people that will see things differently and might find other ways. So yeah, that's the honest answer is that I don't know. Yeah. But I hope it's effective.
Yeah, looks like it. Makes sense. Thank you.
Of course.